Are we going to have a quiz this Friday after the exam?
The exam is Wednesday, right?
Yeah, but this is Friday after.
I don't think so.
Okay.
I'll tell you what, I'll take this into account. Frankly, we went over those things twice, and I know we did this with like Laplace transform block diagrams. We had them in series and in parallel, and then with negative feedback. And that problem, there's a problem in the book this is based on. I was just looking, I couldn't find it, but I'll make amends for this one. First thing I want to do today, though, is go through that problem, and I also want to talk about data windows too. I may come here and do something on the over there too and stuff. Anyway, for the homework problem, for the quiz problem, I want to make sure you're clear on this stuff. Because this is the things, you're going to see problems like this on the test. This is based on just block diagram, negative feedback, positive feedback, series and parallel combinations of transfer functions. So the quiz that you had was this. You had a signal coming in, x of n. Then part of it went straight like this, then it had a multiplier of 1/2 in front of it. Then it came in to something here that well, actually, let me put it with the full feedback loop. This was the feedback loop right here. And you got to get the direction of the signal. It was negative feedback. And this is positive summer here. And this is a summer here too. And this had a factor of z to the -1, and this was 1/2. Y'all recall that? Y'all see it in the quiz? Now, first I want to make sure everybody sees this with feedback, because I did it on the board before the quiz. You have to be sure that this kind of stuff sticks with you. It doesn't matter if you're doing Laplace or if you're doing Z transforms or DTFT. Feedback is feedback. It doesn't matter if it's series, parallel, or if it's negative feedback. So I shouldn't say feedback. If transfer function multipliers, either in series, parallel, or negative feedback, have to be understood. So in general, we're going to do this for the whole class. I'm just going to call this H1 and call this H2. And this is going to be I want to put another stage. It'll just be like this. And this is going to be my Y of n. Now really the truth is, it doesn't even have to be a Y of n. It could be, an X of n, Y, it could be an X of t, Y of t. It can be Laplace, it can be Z transforms. It doesn't matter if it's discrete or continuous. What you have to understand is how to get the feedback on this thing. Now, if you take a transform of this and we go to the Z domain, then this becomes X of Z. That's all it does. After that, that's still a summer right here. Right? This is an H1 of Z, H2 of Z. I'm just going to tell you that these will be in terms of Z because it's discrete time. If it was continuous time, it would be S. It's the only difference. Now, when you look at that, and the signal, well, the signal at this point right here, you should be able to reason through this, and this is Y of Z then. The signal right here is simply H2 of Z, right, times Y of Z. That's the signal at this point. Notice the direction of the arrows, right? That shows the signal. That means right here, you're simply going to take this signal, which is X of Z, and subtract this signal from it. So this signal right here is simply X of Z minus H2 of Z times Y of Z. Please take a look at that. Make sure you can convince yourself that's the signal there. When I start at the output, that's y of z, times h2z, right here. It's subtracted from the input x of z. So here is x of z minus h2z y of z, correct? I made sure I did this on the board before I gave you the quiz one more time. Now, y'all see it? You see it? Now that's being fed in. So this whole thing, this times h1 of z, and that's equal to y of z, correct? Because whatever comes in here, that is y of z, what comes out. Do you agree with that? Does everybody see this? If you don't, take a careful look at this. Make sure this sticks with you for the rest of the time. So that's y of z right here, and that's the equation. Now we have a single function with x of z in terms of y of z, defined as h1, h2 of z. So now we just separate them, and we get the final value. You'll take a look at this right here, and I think I can do it right here. I'm going to drop the z business. So now I have just x times h1, and then I have what? Minus y times h1, h2. That's this times this times this. And that's equal to y. Everybody on this one? Now once I have that, I can take this to the other side. Agreed? I take this term to the other side, and I simply get y times the quantity 1 plus h1, h2 is equal to, and this will be simply xh1. I think everybody, well, we've got to make absolutely certain you see what I'm doing. This is not tricky. Now I need a transfer function. That's the relationship of output to input. That's y over x, right? So now if I want y over x, I take y on this side over x. I call that the transfer function of the entire system. And that's equal to simply h1, which is called the forward gain, divided by the quantity 1 plus h1, h2. And that would be the total transfer function, y versus x, of this system, where this is the input and this is the output. Now you'll notice that this right here, this transfer function, can be used to replace three components, this, this, and this. Do y'all see that, class? With me? I'll adjust that quiz based on the fact that, I don't know what fact, but it didn't seem that tough. I guess I didn't give you I didn't give you a problem exactly like this, so that's fair. All right, now when I take a look at this, I'm just going to use this information, and I'm going to replace, you all see it's negative feedback. I'm sure you see it's negative feedback, not positive. If it was positive, then this would be a minus right there. Correct, class? Make sure you realize that. So now going back to this, I can replace that whole section. And I'm going to do it, I'm going to say that the transfer function from this point here to this point here, call it 2, can be replaced by a single function, or a single transform. And that function would be simply h of z would be equal to the forward gain. Well, the forward gain is just z to the minus 1. Please see this. You agree with that? So that's z to the minus 1 divided by 1 plus the forward gain, z to the minus 1, times the reverse or feedback gain, which is 1/2. So it's going to be plus 1/2 z to the minus 1. Now I can replace that all with that. You follow me? This is the forward gain. This is simply h1. This is h2. Look over here. Forward gain. See the direction of the signal? Right? This is the reverse gain in the opposite direction. Right? Now, the forward gain, it doesn't have to be a number. It can be a letter, it can be anything. It's z to the minus 1. The reverse gain, the amount of signal fed back, is 1/2, and you'll notice it's negative. It's negative feedback. So I can go ahead and multiply top and bottom by z, and now I have z over z plus 1/2, correct? formula right here that we ascertained. It's h1 over 1 plus h1 h2, right? h1 is z to the minus 1. 1 plus z to the minus 1 times h2 is 1/2, right? So that's what we get right here. All right? Yes?
How does that 1/2 at the very beginning before the first?
I'm about to do that, but I have to replace this section before I do. Yes?
I was wondering, why would there be a z on top and not a 1?
Well, that's z to the minus 1, right?
Yes.
Well, if you multiply 1 over z by z, you get 1.
Yes.
Oh, I'm sorry. My bad. My bad. Ah, all right, sorry. You're absolutely right. Thank you. My bad. That's what you get. You're absolutely right. Call me on every mistake I make. So now, only thing I'm going to do to save time is just erase this and replace it with this. Is that all right with everyone? Just the whole thing right here. So I can take this whole thing out and replace it by that. Simply a section right here that has 1 over z plus 1/2. Y'all agree with me? And that goes there. Now, we're back to the next, or first step that I showed you, 2 in series, right? I have this in series with that, which is just this times that, right? Does everybody give me I can just multiply this by 1/2 on top? Follow me and get rid of that first part? So I'm going to do that. I can get rid of that. Just put this as 1/2. Right? And remember, this is x of z coming in here. This is y of z. Well, now I can see that y of z here is equal to x of z times that. So it's equal to x of z times 1/2 over z plus 1/2. And it's that plus just x of z, correct, class? Let me get rid of all this so you can see. It's that plus simply x of z. Do y'all agree with me on that one? I take this times the input, which is x of z, and I'm going to add to that just x of z, right? Do you agree with me, everyone? So that's my y of z in terms of x of z. Now to get the overall transfer function, I have to divide both sides by x of z, and then I get what? I get my transfer function, the overall h of z, which is y of z over x of z, is equal to simply 1/2 over z plus 1/2 plus 1. Agreed? Then I get I did nothing more than divide out the x of z. Then I'm going to get a common denominator. So in doing so, what do I have? Now I have z plus 1/2, and the common denominator in this case is going to be what? It's going to be z plus 1/2 times 1 plus 1/2, or I get simply z plus 1 right there. Don't I, class? I'm just doing it this way, so I feel like it. There's other ways to do it. Does this make sense to everybody? Now, when I do that, what do I actually have? I have z over z plus 1/2 here. That's the first part. Plus, then I have z to the minus 1 times z over z plus 1/2 here. Do y'all agree with me? Right? If you take z over z plus 1/2, that's the first part, plus 1 over z plus 1/2. Well, I don't want 1 there. I need a z, so I have z times z minus 1, right? Agreed? Now, to go back, the inverse of this, I know the inverse of this. This is my h of z. Now I want my h of n. Well, the inverse of this one is simply going to be 1/2 to the n u of n. Does everybody know that? I mean, you got to be absolutely clear on that one. Right, class? What about the next part? Then I have what? Well, I know z over z plus 1/2 is 1/2 to the n u of n, right? When I have a z to the minus 1 in front of it, what happens? I have n minus 1, right? So now I'm going to have this plus 1/2 n minus 1 u of n minus 1. This is one form of the answer. And it's an easy thing. I'm doing it in the most logical way I can do it, in my opinion. One of the things you have to take note is, for that one, I need a z over z plus 1/2 to get the initial transform back, right? And that would be 1/2 to the n u of n. When it's multiplied by z to the minus 1, I know that's going to be a delay operator of 1. Isn't that right, class? Everybody okay with that? All right, now, another way you could do it, right here, if you look just at this, I want you to just focus on this for a second. I know I could do this too. Maybe some of you did it and you didn't get full credit for it. And if you didn't, I'm thinking about you in particular and you. You may have done it this way and not get full credit. But I could also say this is z times z to the minus 1 here, and then I have 1. Well, what takes 1 back? Just delta then, right? So I could have gone this way. I could say now my h of n would be equal to delta of n plus, now what takes this back? Well, I see what? I have z over z plus 1/2, which is 1/2, right, to the n times u of n. Then I have the operator z to the minus 1, which delays it by 1. And I have 1/2 out in front, so I could say I have 1/2 times 1/2 n minus 1 u of n minus 1. That would also be correct. By the way, did you have that and not get full credit? I don't know if, I thought you didn't have the n minus 1.
I have the n minus 1.
You do? You have the delta n too? And the 1/2 in front of it?
Yes.
All right, see me after class, I'll give that. And did you have,
I didn't have the n minus 1.
is that what, I know that there's different forms of this answer. These are only two of the possible forms. There's other forms. You all see how you can multiply that 1/2 in here? Right? And then you get n, don't you? Follow me? Because this is 1/2 of the 1, then you get 1/2 to the n times u of n minus 1. There's other forms of this answer, and we can keep on with every permutation. The way I do it is I evaluate the answer at n equals 0 and 1. And if it's the same as I got, pretty much it's got to be the right answer, but not always. Everybody understand what I did here and why I did it? Remember how to do negative feedback, series, and parallel combinations of transfer functions, okay? That's what I did. Now I asked you to look at a windowing problem. I was going to do some windowing problems I'll show you with MATLAB, but since we have a test coming up that's on the horizon, and the test covers everything, I'm going to get this question, what's on the test? Well, everything legally from the beginning to the end. But the focus is going to be from the last test to the present test. Remember the last test that you looked at, I don't believe we had Fourier series coefficients, did we, on the last test? Remember that?
Do you mean we had the little jigsaw one, or the sawtooth?
Check on your last test. Oh wait, sorry, we didn't have Fourier transform problems, I think. I gave you Laplace transform only, right?
Yeah.
On the last test, talking about that. So on this test, it's going to have Fourier transform problems. It's going to have all the stuff, the other stuff with the DTFT, the Z transform, and everything else from that point onward. Got it, everyone? So please make sure you understand that we're going to be covering all of that. Now, can I take any questions, specific questions? I have stuff I was going to show you, but any questions at all from prior homework or anything like that? Because there's a lot of stuff we covered. Nothing? All right, well, for starters, this is just me telling you, I think duality is one of the most powerful tools that Fourier transforms give you. And duality also allows us to do a lot of things with the DTFT too, right? Remember, duality was a very, very powerful tool. And some of the things that I ask you to do with duality is like find the inverse Fourier transform of some weird looking function. Are you with me on this, class? So suppose, just to revisit this and sort of reanimate some of your brain cells that haven't used, suppose I ask you for the inverse Fourier transform of this. I'm going to say, now I have an x of omega here. This is x of omega. And it's going to look like this. All right, that's my x of omega. And now I want the x of t to create it. Now think about what you need to do. There's a lot of ways to do this one, by the way. First, you see a triangle function, right? So the very first thing you should be thinking about is finding at least the x of t triangle, x of omega equals what?
You mean like
It's going to be a sinc squared function, right? In other words, I'm putting these pairings up here because these are the ones you got to know. So if I have a triangle function in time, right, with tau of t, I know in the frequency domain that's tau over 2 times the sinc squared of omega tau over 4, where tau is the width. That's the first thing I'm going to say, right? Now, what else do you see? You see, there's several ways to do this, by the way. You could work just this side of the fence, you might say, and say, well, the triangle way would be centered here, but it's shifted, right? And a shift operator, now I'm doing this in time, and then we're going to do duality again in the frequency domain. But a shift operator means what? There's going to be a time delay if we're in time. Do you follow me on that, class? We could do it that way, but I choose to do it a different way. Does anybody have a guess what I'm going to do? Go ahead.
Treat it as if it was multiplied by cosine.
Exactly. Remember what a cosine does. If I have, and I'm going to do this all in the time domain before I go to the frequency domain, all right? By the way, this is a classic kind of problem I give. What I'm showing you is one I actually given before. A variant of this. I think it wasn't 1. It might have a height of 2, or something like that, or 1/2. So now I can say this goes to that as such. But I know that if I have x of t times cosine of some omega naught t, the transform of that is 1/2, and it's just x of omega plus omega naught plus x of omega minus omega naught. You all agree with me? Now follow me on this. Now I start thinking about this rationally. Yes.
What made you use cosine instead of sine?
Because sine would be what? J over 2, right? And it would be a minus, not a plus.
I mean, what initially made you say cosine but not sine?
Because I know a cosine waveform always takes the original transform and it simply shifts it up and down by plus or minus omega over 2. It's the same exact shape, just shifted in frequency, and the value of the magnitude is divided by 2. Isn't that right, class? Everybody? Just so you see how the reasoning behind it. You can do it other ways. And I'm showing you one logical way to do this. So now I can take a look at this, and now I know, let me put in some more fine details. Does everybody see the width of this is 4? Agree? So now I'm going to do this. And that would be 2, right? Right here. And then since that's 4, it's just omega. Please follow me. I'm trying to do this logically and slow so you see what I'm up to. Right? What next do you see? Well, I can see the center frequency here is 2, isn't it, class? Right? Now again, this is in the frequency domain. I'm actually, I tell you the truth, I'm going to do something here. Before I go this route, let me do one thing for you, all right? Because we're going to get ourselves, I think we're going to get stung. What I'm going to do is this. I take a look at this waveform right here in the frequency domain, right? And I'm going to make the case if I could get the same exact waveform in the time domain, the same, follow me, versus t, not versus omega, are you with me? Then I could take that and use duality to figure out what it would be in the actual, if this is in the time domain, right, and I get the actual transform over here, then I could say, well, this is in the frequency domain, I could take the transform of this in the time domain over here, and I could adjust it by the 2 pi, and omega becomes minus omega. Do you agree with me on this one? Let me do it, I want to do it this way for a reason, because I want to use that cosine business in a little different way. I'm going to say this. You all see that this is the transform pair if this was time domain, right? Ours is in the frequency domain, right? So here's what I'm going to do. Now I'm going to go ahead and take this, using duality, and I'm going to say this becomes, what, 2 times the sinc squared, not of omega, but of t, right? And over here, then I get 2 pi, right, times this, only instead of t we get minus omega, correct, class? Now, isn't that the same as plus omega because the triangle function is even? That's the reason I'm doing it this way. I want to make sure that I keep this, this is centered right there. So now I'm going to divide by 2 pi, and when I divide that by 2 pi, I get 1 over pi here. And now I can say that that gives me that in the frequency domain, right? I'm going to do it this way. Y'all agree with this right here? As one method? Now that's a triangle, right? So this is like, think of it as our x of omega. And this is like the x of t. Just think that way for a second. Are you with me? Now what I'm going to do is say if I have x of t times the cosine of omega naught t, that renders 1/2 times x of omega plus omega naught plus x of omega minus omega naught. Please follow me on this one. Now here's why I did that, and instead of getting that whole thing in the time domain. It would work that way, but it would be a little more icky. Because I see that if I found out what caused just this function, if I say this is they're calling this x omega, really, I'm going to say this is really like an x omega times the cosine. But if I can find out what causes this waveform, what causes this waveform in the time domain? What in the time domain would give me this in the frequency domain? Follow me? Then I could simply take whatever that time domain function was and multiply it by a cosine function, and then if the cosine function had an argument of 2t, 2 being omega naught, then it would shift it to this point and this point. Do you all see that? Now the height would go down by a factor of 1/2, wouldn't it, class? We're going to adjust for that. You all see that? So follow me on this. Here's my x of t gives me this. I know I need twice that height, correct? Because if over here I got a 1/2. Follow me? Please follow me on this one. So I'm going to go ahead right here and put a 2. I'm just going to put a 2 here, and I get a 2 here. Got me on this? Now I know when I separate it like this, because I got a 1/2 in front of it, the next thing I'm going to do, now that is my x of omega, and this is my x of t. Now what I'm going to do is this. I'm simply going to take that functional form that I have, and I just need to adjust it for omega naught, which is the center point here, which is 2. So I just make this 2. Well, I'll put it as omega naught here, and then I'll just say, therefore, x of t times cosine of omega naught t really renders as 2 over pi times the sinc squared of t times the cosine of 2t. And that gives exactly what I want, and that's going to be a triangle function of frequency domain of width 4 of omega minus 2, or plus 2, plus triangle function of width 4 of omega minus 2. And this is, in fact, the function that would cause it. That's one way to get it. There's probably 2 or 3 other ways. I'm just going to mention some of the others. And all the answers are the same. I mean, when you go ahead and evaluate the function there versus time for any forms of the answers, you'll get the same values. But here's something else I can do. Just listen to me here. Now, I chose to use the cosine multiplier. So really what I needed is the function that would just cause a triangle wave in the frequency domain. And I got that using duality. With me? Please be very attentive here. This stuff is coming at you. Guaranteed duality will be on the next test. So, now, one way to do it. What if it was just this?
If it was centered at like 3, would the cosine just be like 3t?
Yeah, remember, this center point right there is with a shift, right? Originally it was centered at 0, now it's shifted out to that point, class. Everybody see that? It's very important you see it. All right, now what if I just had this function, what caused it? Now think about this logically. The first thing you want to do is what? Let's do this entirely in the time domain. I'm going to erase this so we can. Here's my goal. If I can get this exact waveform in the time domain and find out what frequency domain signature it has, then I can take the frequency domain signature, bring it back to the time domain, right? And then take the time domain signature and bring it out to the frequency domain and replace what? T with minus omega. Do you agree with me? Everybody see that? So we're going to do it this way. I want to find out what function. First I'm going to start with a simple triangle. I know if well, let me do it this way. If I just have this is minus 2 plus 2, height of 1. This is a triangle function of width 4 of t. And now I want to know what the transform is. Well, that's simply tau, right? Tau over 2 times the sinc squared of omega tau over 4. Or the transform would be, since tau is, sorry, this would be 2. The transform of this would be 2 times sinc, right, squared. And since tau is 4, it's just omega. Do you all agree with me there? Right? Now that's like x of t. Now what happens if I have x of t minus 2? What does the functional form look like? If that's x of t, what's x of t minus 2 look like? Shifted and centered at 2. So the whole thing shifts. Still height of 1, right? Well, what's the transform of that going to be? This times 1. If I have x of t minus 2, that goes to what? E to the minus j omega times 2, right? Times x of omega. Isn't that right, guys? Right? It's a simple phase shift, e to the minus j omega times 2. Correct, class? Everybody remember that? So this becomes simply e to the minus 2, or j2 omega times the sinc squared of omega. Now, that is what? That is the exact function we have, only it's a function of omega here, and this is t here. Correct, class? So what I'm going to do is do this. I'm going to do my old duality thing, but I want to make sure you see this perfectly. So now I'm going to say this function in time oops. I'm going to take that one. This is going to be my function right here. And I'm going to just label it as x of t. I'm just going to leave it as x of t, and this is versus time. It goes to, in the frequency domain, this function. And I'm not even going to try to draw it. It's just going to be e to the minus j times 2 omega times the sinc squared of omega. Now you can see the relations. This is my x of omega, correct? Right there. Everybody?
Should it be 2 sinc squared of omega?
Yep. That's my point. Thank you. You're right about that. Are you all with me on this? Now I'm going to use duality. Duality says this function in time, when I bring it over here, I take the small x of t, but now the t becomes minus omega, right? And I have to multiply this one by 2 pi also. And I take this function back to the time domain, and now I have 2 times e to the minus j 2t times sinc squared of t, and it renders this, which is going to be 2 pi times this functional form, which is really going to be triangle function, right? Of with 4 of omega minus 2, right? But what happens to omega here? It replaced with what? I mean, t becomes, that's t over there. It's replaced by, I shouldn't have done it. Minus omega, right? All right, so this is really going to be minus omega minus 2. Now, you'll notice something about this. That functional form, we've got to leave the minus omega in there. It's not something that's an even function. Follow me? When you look at this function, you always evaluate a triangle function. You find out where it's centered. You set this argument equal to 0. Follow me? Minus omega minus 2 equals 0 is omega plus 2 is 0, right? Or omega is minus 2, isn't it? Just do this one. If you have minus omega minus 2, where does it go? It would be what, say again?
It goes to minus 2.
Then this is centered at omega, let me do this. This would be centered at omega equals minus 2, correct? Ours is at omega equals plus 2. Are you following me on this, class? Right? In order to take care of that problem, what happens is, for our functional form right here, we shifted to the right. Now we're actually going to shift the other direction, and this becomes positive right here, right there. That would shift it the other way. I'm just telling you this is what happens. This is the other way, but it would shift it like this. That would be positive. That would be positive, and that's plus 2. And then we have to actually do the whole thing over here too. So this becomes that's plus, and then that comes over here, that's plus. And then this comes this. Then this would be omega minus that. So that would be the actual form that gets that. That's the little tougher one. The reason it gets a lot tougher is right here. I mean, you don't have the luxury of making, disregarding the sign on omega. That's because this is not a symmetric function right here. This is a tougher way to do it, but it is doable that way. You just see the steps though, right? The logical process. I'm doing a lot. I'm spending a little more time on duality than I probably should. Are there any other questions? Because we can go through some more of the Z-transform stuff and DTFT. I want to do one other problem. And it's not related to duality. Remember, with Fourier transforms, all the properties of Laplace apply. Matter of fact, Laplace transforms are Fourier transforms except what? For things that have an existence from minus to plus infinity, right? Then there's a difference. Then you need to actually just do the Fourier transform, or understand the Fourier transform properties. But otherwise, they're pretty much the same. if you have a Laplace transform for a signal that is non-zero only for t equal to or greater than 0, then you can simply take the Laplace transform of that signal and just replace s with j omega, which is nice. Now, some of the other things with z transforms. I did the negative feedback round. Difference equations. Remember, z transforms and DTFTs are literally identical. You just let z become equal to what? E to the j omega, right? That's the big deal to do it. We did quite a few difference equation things, right? Input-output relationships of difference equations, correct? We even synthesized difference equations from z transforms. You all remember doing that? All right, I'm going to do one of those. Suppose I give you h of z is equal to z squared over z minus, z plus 1, z plus 4. All right? I'm doing that way. Now, I want to figure out what difference equation caused that. All right, how do I do that? Well, I know that what? I can go ahead and say this is equal to what? That's y of z, right, over x of z, correct, class? Now I'm going to go ahead and say y of z here would be multiplied times z plus 1, z plus 4, I'm going to do it this way for a reason, times z squared times x of z, correct? Now I multiply out that, and I get y of z here, and I get z squared, right, plus, and then it's 5z plus 5z plus 4 is equal to z squared times x of z. What's my next step? Divide everything by z squared, correct, class? So if I do that, then I get y of z, and it's going to be 1 plus 5 times z minus 1 plus 4 times z minus 2 is equal to simply x of z. And now if we go back to the time domain, y'all know what I'm doing, don't you? I wanted to get it to this point so we're all together on this. Now to go back to the time domain, when I look at that, what do I see? I'm going to have, or the discrete time domain would be y of n, that's the first operation, plus 5 times y of n minus 1 plus 4 times y of n minus 2 is equal to x of n, correct? Y'all agree with that? Now, another thing I could ask for is what is the impulse response to this? What is h of n? How do you do that? This should cover all bases, by the way. Anyone?
Divide by z on the bottom.
First divide by z, right?
Partial fraction.
Numerator and denominator. So then I take h of z by z, right? And I end up with getting z over z plus 1 over z plus 4. That's equal to some, I'll call it a over z plus 1 plus b over z plus 4. Y'all agree with that? How do I go ahead and get a and b? Well, first cover up z plus 1, right? And let z equal minus 1, right? And I have minus 1 over 3, correct, class? So that's minus a third, correct? Y'all agree with that? What's b? And let z equal minus 4, right? So I have minus 4 divided by minus 3 or 4/3. Don't I, class? Not quite there yet. What do I need to do next? Say again? Everybody knows this, right? Multiply both sides by z. All right. First one becomes, look, minus what? 1/3 times
Negative 1 to the n.
-1? Just 1 to the n, isn't it? What's 1 to the n? Well, it's not -1, right? If it would be what, z minus 1, it would be that, right? Don't make that mistake, right? Everybody with me on this? So this is going to be 1/2 times 1 to the n, or just 1, u of n, right? Plus, what's the next one? 4/3, keep going, 4 to the n, u of n. Now, there's two, pardon me? Can you hear what?
Wait, what?
Who's talking? Did you all agree with that?
Yeah.
All right, now, what's the one, there's two ways to sing this, but if you actually, if I asked you if the thing was stable or not, we could go to the z plane, right? And we could say that the first one is at 1, right? Second one is at 4, right? Everything outside 4 is where it converges, correct? But what do we know? Just looking at this, doesn't it blow up? Therefore, it is not stable. Understand, class? It is an unstable system. Make sure you know that. That's very, very important. If you get out of here and go to John Hung's class and you don't know that, he's going to come and talk to you. How did you pass that procedure? Make sure you know that. All right. Covered that. I'm over by. Is there any other questions about the test? It's good. Yes, sir. Let me get him in the back.
Do you prefer us to know like DTFTs or DFTs more?
Well, DFT is a computational technique, right? I mean, DFT has to have, it's what, 2 pi over n. It's going to be what? That's the e to the j, 2 pi over n times nk, right?
Yeah.
All right, now, I may ask you to calculate the simple one, a 4.1. You know, remember we did some of those? But I'm not going to ask you to long, I'm not going to give you a complicated problem with that. It's just to make sure you're exposed to it. That's the only thing I'd ask you. Now, DTFT, on the other hand, you've had exposure to. And the real thing about it is, let me put one thing out with DTFT. And this is something that is included in some of the problems, but it wasn't stated explicitly. Suppose this occurs, just listen to me carefully. I'm going to give you something, an input that's just going to be, say, 5 times cosine, matter of fact, forget 5. Just make it a cosine of omega naught n. All right, that's an input. And I'll go ahead and make it times u of n. I'm going to put it into something, a filter. And suppose I give the filter property as h of z. Now, we can put it in terms of the DTFT very quickly, but suppose I just make it simple. I make this filter property z over z plus 1. And now I want to know my output, y of, say, y of z, and then y of omega, and then y of n. Now, you're going to see what I'm going to do, and you'll appreciate I'm doing this one for you. Now, you can see that this is operating at a frequency omega naught. Do you agree with that? All right. Immediately key in on that. This is at a frequency omega naught. Just remember that. Now, this, if I take a look at this, h of z can be written as 1 over 1 plus z to the minus 1. I'm just restating that. You agree? Then I can substitute in for z equals e to the j omega. So then I have h of omega is 1 over 1 plus e to the minus j omega. You realize I'm doing this as sequentially as I can, logically. Now I look at that. That's a filter, right? Filter has magnitude, filter has angle. I can take a look at this and I can say the magnitude of this would be 1 over magnitude of 1 plus e to the minus j omega. And it would have some angle also of really of this filter property, h of omega. Just let me finish my thought here. Now, what is this really telling us? It's saying that if you have something coming in at a given frequency omega, this will be the magnitude that you multiply it by, get the output, and this is the phase angle that you add to the argument of the constant frequency, right? Follow me on this one, I'm almost done. So just listen to me. I know I got another class looking in, they want to break in, but they're going to stay out. So now, my output right here, just listen, my y of n can be gotten by just taking A, the original thing, then it's going to be multiplied by the magnitude, right here, magnitude of 1 over 1 plus e, the minus j, omega will now become omega naught, whatever that is. Then it's going to be, because that's the magnitude of the transfer function, it's going to be times the original cosine of omega naught n, and then you're going to add to that the phase angle of h of omega naught. Now, the easy way to calculate the phase angle on this one is just use Euler's on that. You can take e to the minus j omega and say that's equal to cosine, they call it omega naught, cosine of omega naught, plus, or minus in this case, minus j sine of omega naught. And chances are omega naught will be chosen, so one of these two will be 0. Suppose omega naught is pi over 2. What's the cosine of pi over 2, a cosine of 90? That would go away then, this would just be minus j. Follow me? Sine of pi over 2 is 1, right? So if you add 1 minus j, the magnitude of that would be 1 over square root 2. The phase angle, 1 minus j, would be what? Minus 45 degrees here. Goes upstairs is plus 45. Think about what I said. I know this is coming at you kind of fast, but this is very similar to what we did when we had Fourier series analysis and we had a transfer function, right? An h, and we took each term and on the output, and we said it's multiplied by the magnitude of the transfer function, and the phase was stuck into the cosine argument. How many remember that? Right? That was with Fourier series analysis for filters, right? All right, I wanted to do that one to make sure. This is part of the stuff you actually did some time ago, but it wasn't brought out on the board like that. All right, it should make sense to you. All right. Now, the test is made up, and I promise you this is the way it's going to be made up. I go through the homework problems, and I find things that are representative of important topics, and I basically manipulate them somewhat. Half the time they're identical. Just look at my old tests. But if you look at my old tests exclusively, you're probably going to get a big, you're going to have trouble, because they're never, well, there are different significant